colors. So here the transition elements, all elements are colored property, okay, because of the presence of unpaired electrons. Here it shows variable oxidation state. Because of the ns n minus 1d, the energy gap is very less. So these two possibilities can take part in a chemical bond formations. Okay, so it shows variable oxidation state. So variable oxidation state and also the presence of unpaired electrons. Okay, if it is the unpaired electron is present, it undergoes dd transition to ground state to excited state, that is T2G and EG set. Okay, the dd transitions it takes place, particularly that element or compound would be a color form. Okay, except for 3D series, scandium 3 plus, titanium 4 plus and zinc 2 plus, because of titanium 22 atomic number, no. So titanium equal to 3d2 4s2. Okay, 4s2. For 4 plus means we have to remove this 2 electron from s orbital, 2 electron from d orbitals. So 3d 0. Okay, so 3d, it attains 3d 0 means there is no unpaired electrons. If it is not unpaired electron is present, there is no dd transition takes place. Okay, so that di 4 plus is a colorless. Okay, and zinc 2 plus also, removal of 2 plus electron attain a that is stable form, there is no dd transition, that is a colorless or white in color. Okay, and complex formations, next property is complex formations. So transition elements can form a number of complex. Okay, number of complex means that is availability of, the main reason is it's a small size, high charge density and availability of d vacant orbitals. Okay, this is the main source to form the complex formations. Okay, because availability of d orbital means the d orbital, the vacant site, so then the ligands donate the pair of electron to this the vacant d orbital to form a number of complexes. Okay, so that is the, when you ask, you can write the small size, high charge density and availability of vacant d orbitals. Okay, so this is already we studied in coordination chemistry also. Okay, so next it is it acts as a good catalytic properties. Catalyst means to enhance the reactions speed of the reactants. Okay, so if the reactant is the speed of the reactants, immediately it will give product. Okay, so here we very well know that in our the d block elements, most of the transition metals are act as a good catalyst. In many, it used for many industries. Okay, so the reason is n minus 1d vacant orbital and variable oxidation state. It shows a variable oxidation state and larger surface area, so that able to form complex formations. Okay, so here this is the temperature versus the time versus temperature. So here its temperature is here. Okay, the activation energy is high, the activation energy of activation is high before using the catalyst. After we can use, this is temperature. Okay, after we can use the any catalyst, its the temperature become less. Okay, so the EA is less, lowering. Okay, so if the energy of activation barrier is lowering, so we can get the product easily. Okay, so because of the powdered form, the reactants easily concentrated with the catalyst. So the role of catalyst is to weaken the bond of reactant ஓட அந்த பாண்டை வந்து என்னது ஸ்ட்ராங் பாண்டை வந்து வீக் ஆகுது. அப்போ ஈஸியாக வந்து பிரேக்கப் ஆகும்போது நமக்கு வந்து என்னது we can get the product. Okay, so this is for the key points you must write. Okay, after that, the last one, interstitial compounds. Interstitial compounds means that is the lattice. Suppose sodium chloride, no, sodium chloride, larger the smaller the cation, larger the anion, smaller the cation, larger the anion, smaller cation, larger anion, because it donate the sorry, it lost the electrons, this chlorine gain the electrons. Okay, positive and negative. So loss of electron it is smaller in size. Gain of electron, it is a larger in size. Okay, the arrangement of packing is like that. Okay, so here smaller, then larger, smaller, then larger, smaller, then larger. So here you see that this is one lattice point. Okay, lattice, here smaller, larger, smaller, larger. Okay, you see here, the some vacants are present. Okay, here the some vacant site are present. Okay, so that voids, so generally we called that is a voids. Okay, so that voids we can filled with smaller atom like hydrogen, carbon and nitrogen. Okay, trapped means that is fillers. Okay, so such time, that is when a small atom like hydrogen, carbon, nitrogen are trapped inside the crystal lattice of metal, so that is a interstitial compounds. That time the crystal lattice, it is a very high and pure melt, and it is a melting point is high and very hard and pure, and it's a good metallic conductivity, and it is a chemically inert. Why? Because of there is no change stoichiometry. இதில் ஸ்மாலர் ஆட்டமை இதுக்குள்ளே வைக்கிறதுனால எந்த சேஞ்சஸும் இந்த இதில் ஆக போகிறதில்ல. கிறிஸ்டல் லேட்டிக்ஸ் அரேஞ்ச்மெண்ட்டில் ஆட்டம்ஸ் அயான்ஸோட அந்த அரேஞ்ச்மெண்ட்டில் தெர் இஸ் நோ ஸ்டாக்கியோமெட்ரிக் சேஞ்ச், எந்த இதுவும் நடக்க போகிறதில்ல. ஓகே, ஸோ தட் இஸ் ஆஃப்டர் திஸ் இண்டஸ்ட்ரியல் காம்பவுண்ட்ஸ் ஆர் வெரி ஹார்ட், பியூர் அண்ட் இட்ஸ் அ குட் மெட்டாலிக் conductivity. Okay, so this is industrial compound. So all the transition elements, the arrangement of lattice point, it contains a small voids. That small voids we can fill the smaller atom like hydrogen, carbon, nitrogen, so we can get the new product titanium carbide and manganese nitride, like that. So this interstitial compounds are very hard in nature. Okay, right. So alloy formations, due to the reason these two, whichever the alloys, the two atoms, it is a similar ionic radii, so there is a no difference. Its ionic radii is a similar for two the homogeneous metals, like for example brass means copper and zinc. Copper oda ionic radii zinc oda ionic radii more or less similar irukanaala easily fit into 1 to 1. Okay, so we can get the new product, that is a brass, and bronze also, copper and tin. Okay, so use this word key point, atomic or ionic radii is similar. Okay, we can get the number of the alloy formations. Okay, stainless steel is a good alloy, and ferro stainless steels, many things. Okay, that's all, these are the properties. Okay, inner transition elements, F block elements. Okay, so today's session we are going to see F block elements. Okay, so generally we can say that inner transition elements. Why it is inner transition elements? Okay, so students, you see here, this is your periodic table. For left hand side S block elements are present, for right hand side P block elements are present, and the middle the D block elements are present. So that the group number 3rd to 12, the D block elements are present. Here you see that this is period number 1, period 2, 3, 4, 5, 6th period, that is the 5D series, that is the 6th period, the lanthanum, the atomic number is 57 and 71. Okay, so after that this is hafnium and the tactinium. So the 57 to 71, the F block, the F orbitals are filling. Okay, so F orbitals, the F orbital, it contains 14 electrons. Okay, so here the lanthanum or the cerium to lutetium, so that is called lanthanide series, and this is the inner, it is present inner, here there is no space, so it is arranged in down in your periodic table. Okay, at the same time the 6th period the actinoids takes place. Actinoids also For actinides onwards, 89 to 103, the 14 elements are present. So this the inner transition F block elements are two types, that is lanthanide series and actinide series. The lanthanide series started from cerium to lutetium, that is 14 elements, and the actinide series started from thorium to lawrencium, this is 14 elements. Okay, and so that it is called inner transition elements. Here there is no space, so it is present down in the periodic table. Okay, so it is called inner transition elements. Okay, right. So this lanthanide, and the lanthanide somewhat it is a d block element, but it's a characters the similar with these elements, so that it is started with lanthanum to lutetium for lanthanide series. For actinide, the properties are similar with these elements, so that it is called actinide series. Okay, so here you see that for lanthanide 14 elements, cerium to lutetium, its a general electronic configuration is 4f 1 to 14, 5d 0 to 1, 6s2. And actinides 14 elements, thorium to lawrencium, 5f 1 to 40 and 60 0 to 1 and 7s2. Students, the series is the 4f 5d 6s2, here 5f 60 7s2. Okay, so here the actinide series, that is it is deleted by our board. Okay, no need to study for this this time for actinides, up to lanthanides only. Okay, lanthanide electronic configurations and atomic trends, oxidation state and properties alone we are going to study, and its uses, that's all. Okay, so these actinides are ruled out for this year. Okay, no problem. Listen here, for here it is, you see, this is for the last shell electron. Okay, last shell, and before that the n minus 1d penultimate shell. Okay, so the fourth period, that is n minus 2f anti-penultimate shell. Okay, so why it is called F block elements? The electrons, the valence electrons or last shell electrons directly entering into the n minus 1 to f anti-penultimate. Anti means here that is inner penultimate shell, so that is called F block elements. So the electrons entering into s orbital, that is s block, p orbital, p block, so n minus 1d orbital, d orbital. So here the inner orbital, that is called F block elements. Okay, so this, it's a configurations already we studied. Okay, and next one, what are the elements present in this lanthanide series? You see here, that is lanthanum, cerium and praseodymium and neodymium and promethium, samarium, europium and gadolinium and terbium, dysprosium, hafnium and erbium, then thulium, yttrium and lutetium. Okay, so these are the elements, 14 elements are present. Okay, and next, trends in atomic and ionic radii of F block elements. Okay, so each time we studied trends. No, here also we are going to study trends in atomic and ionic radii of F block elements. What's happening? Already we studied lanthanide contraction. Okay, so students, what do you mean lanthanide contractions? So lanthanide, see here, this is the lanthanide contractions. For here, this period, for what is that atomic number it started, cerium to lutetium 58 to 71. Okay, for here this series 58 to 58, and the next one 59 and 60 and so on. Okay, so each time the one electron is added to the penultimate cell, one electron is added to the penultimate, in the same penultimate shell. Okay, that is n minus 2 f orbital. Okay, so and the electron also that time proton also increases, so number of protons increases, electron also added in the same penultimate shell. Okay, same inner cell. Okay, inner cell. Okay, so here you see the atomic number is nothing but the proton plus number of electron, proton plus number of electron. So for this series cerium to lutetium, what happened, the proton is added, so that time the nuclear charge is, effective nuclear charge is very high, effective nuclear charge is more, okay, because each time one proton is added, at the same time the valence, the electron also fill in the shells, okay. So electrons are fill in the cells and the protons are added into the nucleus, because of atomic number is nothing but proton plus electron, so that it causes effective, is it effective nuclear charge, that is effective nuclear charge, effective nuclear charge is very high, okay. So the effective nuclear charge is very high. So what's happened here, this proton, it is a positive charge, the filling of electron is a negative charge, so the attractions takes place, okay. So attractions, more attractions takes place at the time, automatically it's a the ionic radii is should become decreases, the size become decreases completely, okay, size become completely decreases, okay. And so lanthanide contraction, this is for the cerium to lutetium, okay. So here you see that down what's happening, for we are studying 3D series and 4D series, 5D series and 6D series, okay. So this is the series, the along the period it is a effective nuclear charge, the size become completely decreases. Down the period 3D, 4D, 5D, 6D, what's happening, okay. So that is called, it arises the lanthanide contractions. So students, what do you mean lanthanide contractions? Lanthanide contractions means, here see here, so lanthanide contractions means the nuclear charge is high and the last shell electrons also, filling of electrons also each time present in the 4D, 5D and 6 in the last electrons. So here the electrons entering into F orbitals, the 4F orbitals are filling, 4F, the F orbitals naturally it is a diffused form, okay. So diffused form means it is spread out here and there, inga anganga appdi irukkudu. So the effective nuclear, each time added the proton and also effective nuclear charge, the effective nuclear charge and the attraction between the last valence electron and the effective nuclear charge is more, automatically size become decreases. But here what's happening now, the presence of 4F orbitals, that is this also electron and this also electrons, so repulsive forces takes place. Electron rendu same kind of charge irukradanaala, so the repulsive forces takes place. So that repulsive forces is somewhat screening effect. Screen இது attraction வந்து என்ன செய்யுது, இது வந்து என்ன பண்ணுது, ப்ரொடக்ட் பண்ணுது, ஸோ ஸ்க்ரீன் ஆகுது. ஸோ தட் இஸ் கால்டு ஸ்க்ரீனிங் எஃபெக்ட் ஆர் இந்த ஷீல்டிங் எஃபெக்ட். இதுக்கு வந்து இந்த அட்ராக்ஷன் இல்லாமல் வந்து என்ன செய்யுது, ஒரு அங்கங்கே டிஃப்யூஸ் ஆகி இருக்கிறதுனால சம்வாட் ஸ்க்ரீனிங் ஆர் த ஷீல்டிங் த திஸ் எலக்ட்ரான்ஸ் the present in the last electron, so screening effect. So that the effective, here you see that effective nuclear charges increases, that is proton charges increases, the nucleus attraction increases as proton increases. Because of added electrons, the proton automatically increases, is greater than interelectronic repulsion increases as electron repulsion. The electron repulsions இருந்தாலும் the same time அது வந்து என்னது, so it is the more effective nuclear charge is more high, so that easily it attracts the last electron, okay. So automatically its size become decreases, okay. So this is called lanthanide contraction. So due to the poor shielding of 4F electrons, the attraction between the nucleus increases and hence at the ionic radii decreases, okay. That is called the lanthanide contractions, okay. So what's happening for this lanthanide contractions, it consequence the similarity of atomic and ionic radii, okay. So here the 3D series, we studied 3D series and 4D series and 5D series, okay, 6D series, Okay, here there is no change. Okay, there is no change for atomic and ionic radii, and but the 4D and 5D, it is a similar atomic and ionic radii. It is a similar atomic and ionic radii. For example, zirconium. Zirconium, its atomic radii is 160 picometer. At the same time, the hafnium, its atomic radii is hafnium, its atomic radii is 159 picometer. So one and the same. Okay, so this lanthanide contractions, what is the consequence? Consequence means அதோட விளைவு என்ன அப்படின்னா, இந்த 4D 5D சீரீஸோட அந்த atomic ionic radii become very similar. So if it is similar means these two elements, the characters and properties are similar. Okay, one and the same properties and similar with that one to one. Okay, so that is a consequence of lanthanide contractions. Okay, so with increase in nuclear charge, the valence shell is pulled slightly towards nucleus. The size of the lanthanum 3 plus ion decreases, so that the cerium to lutetium, the size become decreases, and the lanthanide contractions, the consequence is the 4D, and then there is no change at all for 3D series, but 4D and 5D series, the members of elements present in the 4D and 5D series, the similar properties because of the same, its ionic radii is the 1 to 1 similar with 1 to 1. Okay, so this is for lanthanide contraction. Okay, next oxidation state. Okay, so this inner transition elements, F block elements also, it shows variable oxidation state. Its oxidation state is +2, +3 and +4. But in the common, this series, lanthanide series, common oxidation state is +3 oxidation state. Okay, so for example, for this series, lanthanide series, gadolinium and lutetium. Okay, so gadolinium, the configuration is 4f7, 5d1 and 6s2. It's a +3 oxidation state, means it lost 3 electron. For s orbital, we have to remove 3 electron from this last shell, like s orbital and d orbital. For 2 plus 1 3, it attains 4f7. Okay, so it's the xenon 4f7 half filled stable configurations. At the same time, so we can take the lutetium 3 plus, that is lutetium, the configuration is 4f14 and 5d1 6s2. For 3 plus state, we have to remove, picked up 3 electron from this S and D. So 2 plus 1 3, it attains 4f14. Okay, so for these two elements, for especially for gadolinium and lutetium 3 plus state, it exhibit the stable half filled and full filled electronic configurations. Okay, so this is a extra stability because of the oxidation state in the +3 oxidation state is for half filled, or to determine the stability of the element, half filled or full filled. Okay, so in which are the elements for exhibit the +4 oxidation state. Okay, for cerium and terbium. For C here, the cerium, its configuration is 4f1, 5d1, 6s2. Okay, for 4 plus state, we have to pick up 4 electron. For 2 plus 1 plus 2 plus 1 3, 3 plus 1 4. Okay, so cerium, that is 4f0. So it attains a noble gas configuration like xenon. Okay, xenon core element. So this is a stable configuration. Okay, the same thing terbium also. Terbium, its configuration is 4f9 and 6s2, and this is the removal of the 4 plus 2 plus 2, 4f7. Okay, so this is a half filled stable configuration of xenon core element. Okay, so see here, this is a full fill and half fill in +4 oxidation state. But this series, the cerium 3 plus is the common oxidation state. So this 4 plus, it undergoes the 3 plus state. Okay, 3 plus means for 4 plus to 3 plus. Okay, so that is degrees in oxidation state. Okay, decrease in oxidation state means so that it undergoes the reduction reactions, reduced. So gain of 1 electron, cerium 4 plus is gain of 1 electron to attain the cerium 3 plus. Okay, so that is reduced gain of electron, that is it undergoes reduction reactions, reduced form. It acts as a good oxidizing agent. So see here, this is a cerium and terbium, it is a good oxidant. Okay, so here the E naught value of C, for your understanding purpose, for E naught value cerium 4 plus to 3 plus state, that is the reduced form reduction undergoes, it's the E naught value is plus 1.74 voltage. Okay, so more positive SRP values, it is a good oxidizing agent. We students, we already studied now, more negative SRP values, it is a good reducing agent, more positive it is a good reducing, oxidizing agent. So these two it act as a good oxidant. Okay, right. So and extra for that this series, which are the elements it exhibits a +4 oxidation state, praseodymium and neodymium and dysprosium. Okay, so these elements also it exhibit +4 oxidation state for the oxides of their the concerned metal oxides. Okay, and the next one +2 oxidation state. Okay, so which are the elements to exhibit the +2 oxidation state? For eurobium 2 plus and ytterbium 2 plus. See here, this eurobium, its electronic configuration is 4f7 and 6s2. Okay, loss of 2 electron, that is the stable half-fill electronic configuration, xenon core 4f7. Okay, and the ytterbium also loss of 2 electron, it is a full fill configurations. Okay, so for +4 oxidation state, cerium and terbium, it's a extra stability of to attain the half fill and full fill. For +2 oxidation state, eurobium and ytterbium is a full fill and half fill stable configurations. Okay, so that, so this two ytterbium and eurobium, it is a good reducing agent because of, so it want to convert the 3 plus, so 3 plus 2 plus to 3 plus means increase in oxidation state. It shows it undergoes oxidation reactions. Okay, so oxidation means loss of electron, so increase in 2 plus 2 to plus 3, increase in oxidation state, it undergoes loss of electron, so it gets oxidized. Okay, so oxidized means it acts as a good reducing agent. So this eurobium 2 plus and ytterbium 2 plus, it a good reductant. Okay, so it acts as a good reductant. Okay, so this 2 plus state, it the half fill, it attains a half fill and full fill, and its a reverse reactions 2 plus to 3 plus, it is act as a good reducing agent. At the same time cerium and terbium, the 4 plus to 3 plus, it act as a good oxidizing agent. Okay, so that's all children. For this is for your oxidation state for inner transition element. Okay.